Suppose you are stranded on a deserted island. You take inventory of the items available to you, and you think of what tools you can make to help you survive. There are coconuts on this island, so you'll need a hammer to break the shell. You also notice there are plenty of fish in the sea, so you will also need a spear to catch fish with. Your ideal conception of these tools are not accurate pictures of what you will make, but are simply models of what you have in mind. In other words, form follows the function of the tool. You realize that if you make a hammer, you could always sharpen the handle of it to make a spear. So you decide you'll make a hammer first and later convert it to a spear. We derive meaning from context. In one context where we might see a rock, there is another context where we would view it as a hammer. In mathematics as well, meaning should be contextual. So for example, the additive group of integers can be thought of as an abelian group or as simply a group. Since every abelian group is a group, there is a way to recontextualize it. Category theory forces us to consider objects as instances in contexts. A category can be thought of as a mathematical context where certain internal constructions, based on what kind of context we are in, is possible. We want to stress this. An object is defined by its context and not by its content. A recontextualization, or a construction from one context, aka category, into another context, is what is called a functor. Sometimes we want functors to respect the internal constructions that are available in categories, such as products or limits. But for now, we just want you to think that a functor is a change in context of each object and moves from one category to another category. A comparison between constructions, aka functors, is called a natural transformation. You can also think of it as a secondary construction, as in the example above, where we have a construction of a hammer to a construction of a spear. The diagram which denotes a natural transformation alpha between functors f and g from a category A to a category B is given here. We will formally define what categories, functors, and natural transformations are in the subsequent. Roughly speaking, a category is a directed multigraph, which we will just call a graph, equipped with an algebra of paths. By an algebra of paths, we mean to each finite path is associated a unique arrow. An empty path gives us the identity morphisms, the one paths, the morphisms, the two paths, composition, and three paths, the associativity law of composition. The vertices are the objects in the category, and the arrows are the morphisms. To take a categorical perspective in mathematics means to consider context over content. In other words, category theory is context-rich and content-poor, meaning once the contextual understanding of something has been determined, we may eliminate the complicated content from where this something arose. For example, a group G, given by its content of elements and how the algebraic operations work on that object, can be decontextualized as an object in a category. The internal structure of the group is transformed into the contextual relations between all other groups in the category. In other words, we understand G by context within the category of groups. This does not mean content has no role in category theory. Of course, we need the content to show what context the object G takes. The point is that once this has been done, we can shelve the content and focus instead on the relations. So when one encounters a problem with mathematical significance, the first step is to contextualize it in terms of its mathematical content. This is adding the sense to the problem. Then we isolate the structure involved, which will allow us to define morphism, giving us the object in a context. In other words, we remove the sense and replace it by context. We reformulate the problem by seeing what the problem means, not in terms of the content, but in terms of the context with other objects. This will show us what categorical structure is required to describe the problem. Then if we can solve the problem using this structure, by doing so, we can better understand the problem in terms of the absolutely necessary abstract parts, giving us a way to generalize, make connections with other problems in different mathematical areas, and reinterpret the significance of the result. Since a category is a graph with an algebra of paths, a functor should be a graph morphism which respects the algebra of paths. A category is a context where relations between objects are the morphisms, so a functor is a construction of new contexts or a recontextualization of old contexts. A functor is an assignment of morphisms which preserve zero paths, in other words, the identity morphisms, and two paths, in other words, composition. By using induction, we can then show that all paths are preserved under the functor. Finally, natural transformations are comparisons of constructions. Given a category A and two functors f and g to a category B, a natural transformation is a collection of morphisms in B which connect paths constructed by f to paths constructed by g on the same objects. It is verified by showing the resulting squares each commute. And a commuting square means that the two paths f followed by g and f prime followed by g prime result in the same morphism. So in this series, we will give an in-depth introduction to category theory. However, these videos should be supplementary to a more proper introduction to category theory.